here is the outline for the chapter 23. So we will introduce a variable called electric flux. And then based on this electric flux, we can write out the Gauss law. Actually, this is called law. We will not prove it. We will not prove it. For theory one, we can prove it, but for law, we just tell you what it is. And using the Gauss law, we can simplify some of the calculation. In chapter 22, we try to calculate the E field generated by some structure, like the charge ring, charge disk, and we need to separate the continuously distributed charge into many small packets, and then we try to find the E field generated by a small packet and try to integrate all of them to find the overall E field. And here we make use of the Gauss law. The Gauss law behind is actually the surface integral. But if there is some of the structure is symmetric, and we can apply the Gauss law and then we can simplify the calculation. But we need to understand what is the surface integral to fully make sure of it to find the E field generated by some specific structure, like a cylindrical symmetric, planar symmetric, or spherical symmetric, something like that. Okay, so this is the overview of the electromagnetic system, or the overview of this semester. In chapter 32, we will have a chapter called the Maxwell equation. And of course, this equation is not actually the same as what we see in this textbook, but it's just a demonstration. So in this chapter, we will learn Gauss law. And of course, in this textbook, we only use the integral form rather than the point form or differential form. But actually, in chapter 32, I will also give some supplementary notes about the differential form. And I suppose many of you are civil engineer students. You might not use Maxwell equation later, but I'm not sure whether you will learn the fluid dynamics. Fluid dynamics will use something like the curl divergence, like this. Oh, it's just like, a triangle upside down. What is that? At that time, I will try to tell you what it is. So, actually, in this chapter, we will learn the Maxwell equation, and also in chapter 32, we will also introduce this one. This is the Gauss law. This is the Gauss law for magnetic field. And in chapter 29, we will learn the Ampere's law. In chapter 30, we will learn the Faraday's law. So, yeah. So this one related to the magnetic field generated by the current or displacement current. And this one is the magnetic induction, which means that if we have time varying magnetic field, it will generate electric field like this. Okay. So here we firstly introduce the electric flux. So Gauss law related to the electric field at point on a Gaussian surface or closed surface. So in this textbook, it usually call the surface Gaussian surface, and this Gaussian surface refer to closed surface, 封闭. To the net charge enclosed by the surface. So closed is something like that. If the surface without a hole, then yeah, this is closed. If I try to open it, this is open. This is closed. So very easy concept. So which means that if a surface does not have a hole, then it is closed. Okay, so now we try to consider the how to define the electric flux. Of course, this is just a demonstration. So, but Actually, it's like if we have a charge here, and of course this is a positive charge. If it is a positive charge, in the previous chapter, you know, if it is a positive charge, it will generate some E field pointing outward, So now we try to consider a sphere, with a center here, and then with a certain radius. And then we try to see, this is the electric field line. And in the previous chapter, you know, if we have more arrows, or if the electric field line are more dense, then the electric field at that region is stronger. So now we try to draw a circle to see how many electric field lines go through this Gaussian surface. Of course, this is just a 2D picture, so it's just like a circle, but actually should be a sphere rather than a circle. Okay, so now if it is if we have a charge Q, then we can count totally 1, 2, 3, 4, 5, 6, 7, 8. Totally 8 arrows going through this circle. So we count 8 electric field lines. So now suppose we have a 2Q. Suppose this Q is this charge is larger, then we can count 1, 2, 3, totally 16. Totally 16. I don't count it one by one, but actually it should be 16. Going through the same circle, or the same sphere, going through the same Gaussian surface. And then here, if we have a negative 0.5 Q, negative half of Q, we can see that if it is a negative Q over 2, then there should be some E field pointing inward. In that case, we will count this number to be negative 4. So we always define outside, pointing outside to be positive, pointing inside to be negative. Mathematically, we always define the sign for inside outside like this. For outside positive, for inside negative. So this is positive 8, positive 16, and if this 4 arrow pointing inside, it is a negative 4. So if we try to count the electric field line over the Gaussian surface, if the charge is larger, then we can count more electric field lines. If it is a negative charge, we can see the electric field lines are pointing inward, which is a negative number. So so we try to relate this so-called electric flux with the charge amount, because this is actually not electric flux rigorously, but it's just an analogy. But at least we know that if we have a larger charge, we can count more arrow. And if it is positive charge, the arrow are generally pointing outside. If it is a negative charge, the arrow pointing inside. Okay, so here we try to define the electric flux rigorously. So first we define what we call area vector. So area vector is of course a vector. So for a vector, we should know the magnitude and also the direction of a vector. So for the magnitude, it is easier to understand, because the magnitude of an area vector is the area itself. So it is trivial. And also, we also need to define the direction of this vector. So the vector that is perpendicular to the element, So suppose this element is a rectangle. We can just count it by the width times the height, or if it is or if it is a curvature, just like a sphere, then we need to separate it into many small parts, and then we can just regard it as a flat surface. So now we need to determine the direction. The direction is actually perpendicular to the element. So this is the element, and the direction is perpendicular to it. So you may say that, suppose this is a plane, if you consider the line perpendicular to it, maybe you can consider DA may be pointing this side or maybe pointing that side. So if it is just an open surface, then it's okay. You can just define the direction depends on what you like. But for the closed surface, we always defining the DA pointing outside of the closed surface, just like here. Outside is positive. So we also define DA, which is perpendicular to the element and also pointing outside. So yeah, so here the electric flux is then d phi. The electric flux is d phi, so it is defined by through a patch or element with area vector dA is given by a dot product. D phi is the electric flux, E field is the E field at that point, E field at that point, dotted with dA. So maybe for this case, dA is defined pointing to the right side. So this is dA, and then E dot dA. So E dot dA is E is the magnitude of E vector, and then dA vector is the area of that part. Maybe we can write it as a delta A or dA, and then dotted. The dotted for two vectors, we need to multiply by the cosine theta. Theta is the angle between these two vectors. Okay. So if theta is between 0 and 90 degrees, then cosine of theta is positive, and so as the electric flux is positive, just like what I've mentioned. So it's like the E field is have a similar direction with the dA, and dA is always pointing outside of the Gaussian surface. And if theta is 90 degrees, which means that E is perpendicular to dA. Then cosine theta is 0. The flux is 0. And if cosine theta is between 90 and 180 degrees, then cosine of theta is negative. Then we will have a negative flux. Okay. So here, now we will try to consider the total flux by integrating the dot product over the full surface. So the total flux through a surface is given by this integral. So just now we just try to suppose this is the Gaussian surface. It's just like a heart. It's just like a heart. So this is the Gaussian surface we define, and then we try to divide this Gaussian surface into many small area, and then we can find d phi for each part. And then we try to add all of them together so that it is the total flux phi. And of course, we have infinite many small areas, so we need to use the integration, which is like the Riemann sum in the calculus class. So we use this integral E dot dA to define the total flux. So for the total flux, it does not necessarily apply on closed surface. It can be applied for arbitrary surface, the total flux. So we only use the normal integral sign here. But for the Gaussian surface, for the closed surface, or we can call it Gaussian surface, then we call it net flux. So this one is a Gaussian surface, and here we draw a circle here to specify that this is a closed surface integral. Yeah, for this textbook, it always use a single integration sign for this one. But for mathematics textbook, sometimes it would be written as like this, E dot dA, to specify it is a double integral. It is a double integral or a surface integral. Use a double integral sign. So here it will be something like this to specify the closed double integral. I'm not sure whether here, just no, it still use a single integral sign. Yes, the notation for mathematics and physics are somehow different. Okay, so this is the definition. And of course, the SI unit for the net flux is, or the total flux and net flux are the same. So the SI unit for it is, this one is for E. For E, the SI unit is N over C, newtons per coulomb, and dA is meter square. So the SI unit for the flux will be Nm square over C. So this is the definition of the total flux. And as I mentioned, if phi is larger than 0, then it means that the flux is going outward. If phi is negative, the flux is going inside to the Gaussian surface. An analogy is like, you can also define the Gaussian surface to be this classroom. And then, of course, this classroom includes all of us here. If we try to count the flux for people, then you should try to count. If someone is going outside of the classroom, then the flux of the people is positive. If someone is going inside this classroom, the flux is negative. If the flux is 0, there is no one going inside or going outside, or at the same time there are same number of people going inside and going outside. They cancel each other. The number cancel each other. The flux there doesn't necessarily all the way going outside or all the way going inside. Maybe part of it is going outside, part of it going outside. So part of it will be cancelled. So this flux is an average value. So it tells you maybe for some time 4 of the people going outside of the classroom, and at the same time 3 people going inside the classroom. Then the net flux is 1, something like that. So far, any questions? This is a new concept to talk about. And if you have questions, just feel free to ask. Otherwise, we'll go to the Gauss law directly. Yeah, maybe, yeah. So here is just talk about if we have a Gaussian, so this is the Gaussian surface. If we have E field generally going outside, then we will call this flux to be positive, because we also define dA perpendicular to the surface at that point and also pointing outside. So we will have E dot dA to be positive value. E dot dA to be positive value. E dot dA. And if it is a phi to be negative, it is somehow like the E field pointing inward. The E field pointing inward. And we still define dA pointing outside. dA are always pointing outside, or dA pointing outside all the way. So in this case, dA and E are pointing to the opposite direction. In that case, E dot dA should be a negative scalar. After the dot product, it is a scalar. For cross product, the output is still a vector, but for inner product, it is a scalar. This one should be a scalar. Okay, any questions? Okay. Okay, we have a sample problem here. So here it says a Gaussian surface in the form of a cylinder of a radius r immerses in a uniform E field. So the E field is pointing to the right side. With a cylinder axis parallel to the field, what is the flux phi of the electric field through this closed surface? So this is a good example to demonstrate the idea of the net flux. Okay, so now we try to consider the total flux for this Gaussian surface as a cylinder, and actually we can write it like this. So it includes this side, the top, the bottom, and the side. So the top is A, the bottom is C, the side is B. So it can be separated as E dot dA for part A, and then E dot dA for part B, and then E dot dA for part C. We can separate the whole integral in 3 parts. Okay, so first we try to consider E dot dA for part A. For part A is actually this part. Okay, so dA pointing outside perpendicular to this element, so it points to the left side. E point to the right side. So E dot dA should be E dot dA. E dot dA is E times A times A. A is actually this area of the circle, the area of the circle, and then cosine of theta, cosine of 180 degree. So this one is -1. So we have this one to be negative EA. So let's go to C, part C first. Part C first. Because the arguments are similar. So for part C, dA point to the right side, which is pointing outward, and E field point also point to the right side. So E dot dA is EA cosine of 0 degree. So it should be E times A, like this. So the remaining part is E dot dA for part B. For part B, E is pointing to the right side, and dA is always perpendicular to it. So for this point pointing upward, for this point pointing out of the page, for this point pointing backward, always perpendicular to the E field. So we should have E dot A to be E times A cosine of 90 degree. Cosine of 90 degree is nothing but 0, so this is 0. So we plug this one there. So finally we find that it is a negative EA plus 0 plus EA. So the net flux is 0. Very, very beautiful number. Okay, any questions? If no questions, that's all for today, and I'll see you next week.